Hello, this is the second knowledge clip of chapter 5, and in this knowledge clip we are still continuing with the chemical potential mu, but this time part 2. So what I will tell you in this knowledge clip is how the chemical potential depends on the concentration. A brief recap to begin with. So a free energy change is given by this formula where we have a temperature dependent term, a pressure dependent term, and new last knowledge clip was the term that depends on the amount of moles added or taken out of the system times their respective chemical potentials. At constant pressure and temperature, the first two terms are zero, and we only have the amount of moles going in or out of the system times their chemical potentials. We looked at this example where we had a high concentration of these blue molecules in this inner region and a low concentration of the blue molecules in the outer region. Then a spontaneous change leads to the uniform concentration distribution of the blue molecules, and that state is now corresponding to the equilibrium state, while the first situation is the non-equilibrium state. And we found that at non-equilibrium, the chemical potential inside of the box is higher than outside of the box, and we concluded that there's a movement of molecules from high to low chemical potential. It's actually quite similar with heat flow. When you have a region that has a high temperature and a region that has a low temperature, the heat flows from the high temperature to the low temperature. The chemical potential is analogous like the temperature, just not for temperature but for the amount of moles. Interesting, no? Good. At equilibrium though, we found that the chemical potentials of the inner compartment and the surrounding are the same, right? So that's the equilibrium condition, that the chemical potentials are the same. So we also learned that the free energy change resulting from the transport of molecules times their respective chemical potentials gives the maximum amount of non-volume work, and that is effectively used by the cell with these membrane proteins to rotate a shaft due to the concentration gradient of protons that then leads to the synthesis of ATP. Now I want to answer the question, how does the chemical potential actually depend on the concentration? Because previously we only spoke about there is a chemical potential at different concentrations, but we didn't know how it depends on the concentration. That's what we are going to figure out today. Okay, in the following we will develop a model that will give us an expression for the chemical potential dependence on the concentration. So the model is based on this grid. That grid is filled with these black circles and these white circles. The white circles are the solvent molecules, and we call them component 1 in the following. And the number of solvent molecules is given as capital N1. The black circles are the solute molecules, which we call component 2. And their number is given as capital N2, of course. So the total number of molecules in this grid is simply the sum of the solvent plus the solute molecules, as simple as that. The solute molecules are dilute. That means there's an excess of solvent. Simply that means the solvent molecule number is much larger than the solute molecule number. So to calculate the free energy of both the solvent and solute molecules in this grid, what we do is we first take into account what is the value of the free energy of the solvent molecules in their pure state, plus the number of molecules of solute molecules times their chemical potential, again at their pure state without being mixed with the solvent. And again, these two chemical potentials with the stars are the chemical potentials per molecule, that's why there's a bar on top, of pure components indicated by the star 1 and 2 at standard state. And so this is just the chemical potentials of the pure molecules. So they are not mixed with each other, right? So it's like a construct where those molecules are not mixed with the solvent and solute molecules. And to consider for the effect of the mixing on the Gibbs free energy, we introduce that term, the Gibbs free energy of mixing. So the Gibbs free energy of mixing can be calculated as follows. with the formula that we always use for the Gibbs free energy. The enthalpy change of mixing minus the temperature times the entropy change of mixing. So here we are considering an ideal solution. That means solvent and solute molecules do not interact energetically, right? When they now hop around on this grid and they come closer, there's no repulsion or attraction between them. There's no interaction, and that allows us to cancel out delta H mixing, no enthalpy of mixing, because attractions and repulsions between solvent and solute molecules would result in an enthalpy of mixing. But we don't have that here, so that term is zero. Therefore, in an ideal solution, the Gibbs free energy of mixing is simply given by the second term, the negative temperature, times the entropy of mixing. So now we need to figure out what is that entropy of mixing. The entropy of mixing can be calculated just by the difference of the entropies at the mixed state, which is the later state, minus the unmixed state. Okay? So the mixture entropy basically is what we will now obtain an expression for, but the unmixed state are simply the corresponding entropies of the two pure components, the solvent and the solute at their pure state, indicated by a star. So we know an expression for the entropy already from Boltzmann, from Ludwig Boltzmann. He introduced that formula that gives the entropy as a function of the multiplicity W, which we spoke about in earlier units of the class. So we can now express each individual entropy with the corresponding Boltzmann expression. And we factor out the Boltzmann constant here, and then write in parentheses ln of the multiplicity of the mixture, that is this entropy term, minus the natural logarithm of the multiplicity of the pure states, W1 star and W2 star. Yeah? Those are subtracted from the mixture entropy. Okay, so what is the state, the multiplicity of the unmixed, the pure solvent? It's just 1, because there's only one way. There is no mixing possible. There's no different rearrangement possible. The multiplicity is simply 1. There's only one possible state that the pure component has. Same for the solute. It's also 1, right? So those two terms here, basically taking the logarithm of 1 is 0. Nice, right? So those two terms here will be 0, and we will only have the logarithm, the natural logarithm of the multiplicity of the mixture. The multiplicity of the mixture can be calculated with this formula. And the origin of this formula you can find in the molecules of live bulk. So the multiplicity of the mixture is given by the factorials of the total number of molecules in the mixture, being N1 plus N2, right? Divided by the factorials of the number of molecules of the solvent times the factorial of the number of solvent of the number of solute molecules. That's the expression for the multiplicity of the mixture, which we now can plug in to the definition of the entropy. So then we simply get, for the Gibbs free energy of mixing, which is only composed of the entropy term, that the logarithm part here is given by this expression for the multiplicity, having plugged that in into the multiplicity definition for the mixture, right? So that's what gives us now an expression for the Gibbs free energy of mixing. Excellent, we can use that expression up here now. So now that we have that expression for the Gibbs free energy of mixing, given by the Boltzmann term here with the multiplicity expressed by the factorials, we can just plug it in to this expression up here and write it again. G equals the pure unmixed solvent and solute minus the enthalpy, the free energy of mixing term here, which was plugged in for here. Okay, remember our goal was to obtain an dependence of the chemical potential on the concentration. That's our goal. So now we know how the free energy of the total system can be expressed with this formula. Now, to get an expression for the chemical potential, we remember that the chemical potential is defined as the partial derivative of the free energy with respect to the amount of molecules being added or subtracted from the system. So for the solvent, component 1, we can write the partial derivative with respect to the amount of solvent molecules being added or subtracted at constant pressure, temperature, and solute number of molecules being also constant. Same goes for the solute molecules, and their chemical potential dependence is also the partial derivative, but this time with the free energy change with respect to the amount of solute molecules and at constant pressure and temperature and constant solvent molecules, component 1. Okay, now I'm actually going to skip a few mathematical steps, because what we need to do now is we basically need to take this expression here for the free energy, plug it into the partial derivatives here, and then take the partial derivative. So just calculus that would be done. And since there are these factorials, those can, as we learned earlier, be replaced by this Stirling approximation, because for very large numbers of the factorial, it's not possible to calculate them anymore because the numbers get so huge. So the Stirling approximation plugged in allows us then actually to really take the derivative of the free energy. And I don't do this here, I just give you the end result, which for the chemical potential of the solvent is given by this formula. The chemical potential per molecule of the solvent is the chemical potential per molecule of the solvent at the pure state, which is indicated by the star, plus this term, which is the Boltzmann constant times the temperature times the natural logarithm of the mole fraction of the solvent. So X is the number of solvent molecules divided by the total number of molecules. That's the mole, or the mole fraction. And exactly the same formula, of course, for the solute molecules. The chemical potential for pure solute plus this mole fraction dependent natural logarithm term, where X2 is simply the number of solute molecules divided by the total number of molecules in this box here. And again, this bar here indicates for us that this is the chemical potential per molecule, not per mole, but per molecule, right? Okay, so now with these expressions, we can also write formulas for the chemical potential of the solvent and the solute per mole rather than per individual molecule. And those can be obtained by simply exchanging the Boltzmann constant with the gas constant. So in the following, we will mainly focus on the second expression, the chemical potential of the solute, because that's what we are interested in. Remember the example with the blue box and the block box with the blue molecules in it. Those blue molecules are solute molecules that distribute over time over the whole volume. And that's also what we are interested in the cell, basically. How do dissolved molecules in the cell, solute molecules, what are their chemical potentials? But first, let us be aware that for the solute, this parameter here is the chemical potential of the solute in the pure state, meaning the mole fraction is 1. 100% is pure state. In biochemical thermodynamics, however, the standard chemical potential of the solute is usually at a concentration of 1 mole per liter and not at the pure state. So I would like to express this here with the standard chemical potential instead. Only for water is the chemical potential at standard state actually the chemical potential of the pure water, which is 55.6 mole per liters. Okay, so let us obtain a concentration dependence of the chemical potential rather than a mole fraction dependence, which we have there. So I write again the chemical potential of the solute, and we know that is given here as the chemical potential of the pure solute plus the second term that gives the dependence on the mole fraction. So here I left some space because now I will just plug in there plus RT times ln x2 standard minus RT times ln x2 standard, right? This subtraction is basically 0, so mathematically that is fair to do. Then this first part here, I put them into a bracket, being the chemical potential of the pure solute plus the concentration dependence of the solute at standard condition. And the second part here, I combine these two terms now, being then gas constant times temperature times the logarithm of the subtraction of the two logarithms, which gives a single logarithm where we just divide the mole fraction of the solute in the solution with the standard mole fraction of the solute. Okay, so if the solute component 2 is dilute, then we can write the concentration of the solute rather than the mole fraction by moles of solute component 2 per cubic meter or per liter of solvent and solute. But if it is dilute, the volume of the solute will be really small compared to the volume of the solvent. And therefore we can approximate the total volume just as the volume of the solvent, component 1, right? Now, the molar volume is written as V bar 1 for the solvent. That's the molar volume. And it has the unit cubic meter per cubic meter solvent per mole solvent. And you can see now, if I multiply C2 in this approximated form with the molar volume of the solvent, then the cubic meters here and there, they cancel out, and all that will be left is the mole of the solute per mole of the solvent, right? And that is basically a way to express the mole fraction with molar volume and concentration. See it at the units. So then the expression of the mole fraction ratio that is here in the second term can be written with this multiplication of concentration of solute times molar volume of solvent in this actual solution, and then again at the standard state. And these two molar volumes, they cancel each other out, and all that will be left are the two concentrations. So I can actually really simply replace these two here for a diluted solution with the ratio of the concentrations of the solute. So giving us now the final equation of this derivation, the dependence of the chemical potential of the solute, component 2, on the concentration of the solute. That is a very important equation that is used in biochemical thermodynamics all the time to predict the chemical potentials in dependence of the concentrations. So that's why I put it in a little gray box here. And you see the first part of the equation comes from the standard chemical potential of component 2 being the pure solute plus the concentration dependence of the solute, which then allows us to bring it to the standard state, which is 1 mole per liter. And the second term is simply the concentration dependence that was obtained by replacing the volume, the mole fractions with the concentrations. Okay. That brings me to the summary of this knowledge clip, which is first we found an expression that gives us the Gibbs free energy of a two-component mixture. That expression was the following. It is written here, where there are first two terms which correspond to the pure unmixed solvent and solutes, and the second terms are the free energy of mixing. We found that in an ideal solution there are no energetic interactions between solvent and solute molecules. That allowed us to obtain an expression for the free energy of mixing that solely depends on the entropy of mixing. And last, we found a relative concentration dependence of the chemical potential with respect to the standard state, which is this very important formula where you have the natural logarithm being applied to the concentration ratio of the actual concentration divided by the standard concentration. And we will use this expression also in the next knowledge clip to obtain expressions for the equilibrium of a chemical reaction actually. Until then, thank you for your attention.